Hello, class. This is Mr. Hart. And in this podcast, I want to continue on gravity and orbits. And if you remember last time, we talked about centripetal force, okay, in the last podcast. But you may be wondering, what does this have to do with gravity? Okay. And before we can really get into that, we have to have a better understanding of what gravity actually is. Okay. Now, you may know that, things fall, things get pulled to the ground, right, because of gravity. But you may not realize that there's actually gravitational force between all objects that have mass. Okay? So this idea is called general gravitation or universal gravitation. Okay? It's the idea that all objects have a gravitational pull towards all other objects. Okay? So anything that has a mass is going to have a gravitational pull. So does that mean any two objects? Okay, is there a gravitational pull between my remote and my hand? Okay, turns out there is. It's not very strong because my hand's very small and the remote's very small, so the gravitational pull is very small, but there is still a very small gravitational force. So it can be any two objects. Okay, it can be the sun and the moon, the sun and the earth, me and the earth, me and the moon, the water on the earth and the moon. Okay, my remote and my chair and my computer and my phone. Okay, they all have a gravitational pull towards each other, but it's just going to be really small because the objects are so small. Okay, so in class we did this gravity force lab. Okay, we asked, how do mass and distance affect the gravitational force? Okay, so hopefully you had a chance to do that online if you didn't already. But what we learned is that mass is proportional to the gravitational force, and distance is inversely proportional. Okay, so as mass goes up, the force goes up. As distance goes up, the force goes down. Okay, and so we can write this idea in this equation. So this is the general gravitational force equation for any two objects. Okay, so the gravitational force is equal to big G. We'll talk about that in a second. But this is just a constant. Big G times the mass of object 1 times the mass of object 2 over the distance between them, or the radius between them, squared. Okay? So again, the force is proportional to the mass, like we discovered, and is inversely proportional to the distance, or the radius. Okay? And so this is a very important equation. This is one of Newton's, fundamental equations, showing that any two objects' gravity can be calculated by finding their two masses and the distance between them. Okay, so you should know this equation very well. But let's talk about this big G. Okay, so this constant determines how much of the force there is. Okay, and as you can imagine, for gravity, this is going to be a very small number, because if you have a 10 kilogram object and another 10 kilogram object, okay, and a short distance, it's still a very, very small force. This means this G has a big part of it, or I should say a very, very small part. So if you want to look at the actual number, this universal gravitational constant, this big G, is equal to 6.67 times 10 to the negative 11th. Okay, and then these units just make it so it ends up in newtons. But think about that, 10 to the negative 11th. Okay, that's a really small number. Okay, if this was in just meters, it'd be smaller than the radius of an atom. Okay, so this is just very small. Okay, so for any two numbers, we had times it by 6.67 times 10 to the negative 11. Okay, so that's why it's hard to have strong gravitational pulls, because they need to be so big. Okay, so this universal gravitational constant is what comes into effect. Okay, but let's just try and calculate the gravitational pull between two objects. Okay, so we have an object with a mass of 1,000 kilograms and an object with a mass of 5,000 kilograms, and they're 2 meters apart. What's the gravitational force between them? So we know mass 1, okay, it's 1,000 kilograms. Okay, we know mass 2, okay, it's 5,000 kilograms. Missing again, I apologize for the sloppy handwriting because I'm writing with my touchpad. And then we know the distance between them, or r, is 2 meters. Okay, and we want to find the force. So let's remind ourselves what big G is. Big G equals 6.67 times 10 to the negative 11. Okay. So we know that the force equals big G times M1 times M2 over R squared. Okay. So let's plug it in. So we got 6.67 times 10 to the negative 11 times 1,000 times 5,000 over 2 squared. Okay. All right, so I'm going to pull out my calculator for this one since I cannot do this on my head or in my head. Okay, so 6.67 times 10 to the negative 11 times 1,000 times 5,000 divided by 2 squared, or 4. Okay, and so we get, if I did this right, we get 8.334 times 10 to the negative 5th. Okay. And again, this will be in newtons. All right, so, and again, make sure you do that in your calculator correctly. There's a lot of places to make a mistake, but if I did this right, you get 8.34 times 10 to the negative 5th newtons. Okay, so 10 to the negative 5th newtons is still really small, right? That's that's a few millionths of a newton. Okay, a few millionths of a newton. So, these are two fairly large objects, 1,000 kilograms and 5,000 kilograms. Okay, you're talking about around 2,000 pounds and 10,000 pounds. Okay, this could be a car and a big truck or something. And the gravitational force between them is still just a few millionths of a newtons. Okay, so we have to have some really large objects before we have really a strong gravitational force. Okay, so hopefully that gives you a idea of how much force you actually need, okay, or how much mass you actually need to have a strong gravitational force. So again, even though we say every object has a gravitational pull between them, for most objects we can kind of ignore it because this gravitational pull is so small. All right. Well, let's say it's not, or the masses aren't so small. Let's say we have, for example, Mercury and the Sun. Okay, Mercury is a fairly large planet. The Sun's a fairly large planet. Okay, and if you look at their mass, it's 3.28 times 10 to the 23 kilograms, and the Sun has a mass of 1.99 times 10 to the 30 kilograms. And Mercury is 58 gigameters away from the Sun. Okay, giga meaning a billion, right? 58 billion meters away from the Sun. And so, I'm not going to take the time to do this in this podcast because it takes a while to write out. But go ahead and try this if you're doing this for participation. And you'll see that you have the bigger numbers, okay, the 10 to the 23 kilograms, the 10 to the 30 kilograms. Even when you have this very large distance, 58 billion meters, you'll still get a fairly strong gravitational force. So if you have these large masses, you will have enough mass to get the strong gravitational pull. Okay, so that's why we usually only think about gravitation when we're thinking about planets, okay, and other large objects. Okay? All right. Let's move on. Okay, so then we did watched this video that talks about how much the Earth weighs. Okay, you can find it here. And we also calculated it ourselves. So think about it. You could do this just using the information we know and that equation. So if we know the gravitational acceleration is 9.8 meters per second squared, and we know the radius is 6.4 million meters, and we know that we weigh 1 kilo, or an object weighs 1 kilogram, or whatever. we can actually use these numbers to calculate it out. Because if you use the gravitational acceleration, it turns out you can find the gravitational force. And so you would set it up like this. You'd say, my weight is the same as the force the Earth puts on me, right? So my weight, we'll call it M2, okay, times G is my weight, right? That's my gravitational force. Well, that has to be equal to Newton's law of gravitation, right? So M1 times M2 over R squared, okay? M2 is going to cancel out, okay? And so we're left with the gravitational acceleration is equal to big G, so small g, gravitational acceleration is equal to big G times M1 over R squared. And so you can actually solve this for M1, which would be the mass of the Earth. So it's actually really cool. You can actually solve for how much the mass of the Earth should be based on these numbers, and you get the actual mass. You can check it online. So again, I recommend doing this if you haven't already to see that you can actually calculate the mass of the Earth. Okay? So really cool that this equation has so much power. We can use it to calculate these things. Okay? All right, and then the last thing we talked about was how do we know the value of big G? Okay? Because it's a really small number. Okay, we can't just take two objects, let them sit on the ground, and see how long it'll take for them to hit each other because the gravitational pull isn't that strong. Okay? And so it turns out that we need a man named Henry Cavendish to figure this out. So Henry Cavendish was kind of a strange character. He didn't like people at all. Okay, he had some strange methods for his experiments. Back then, he was experimenting with electricity, and they really didn't have a way of measuring current. So he'd stick his hand on the current on the wire, and it would basically electrocute him. Okay, it'd shock him, and he'd basically feel it, see how much pain he was feeling, and use that to determine how much current was going through the wire. So he'd just practice and practice feeling the different pains that he'd get from the different amount of currents until the point that he could just hold the wire and say, oh, I'm feeling this much pain. This must be, a 500 microamp current or whatever it was, So it was kind of crazy that he could use, his own pain to determine how much current was going through. So kind of a strange dude, some unorthodox methods, but he is very famous for the Cavendish experiment, which was fundamental and just super important for understanding gravitation, having this constant. Because what he did is he basically he had a bunch of lead balls in this, garden shack in the back of his yard, okay? And he hung them from this wire, okay? Kind of like a dumbbell if you want to think about it. So he had two on this dumbbell and two on the outside, and then let the dumbbell naturally rotate under gravitation, okay? And this little mirror on the string would rotate as well, okay? So he didn't want to be in the room because he didn't want his own gravitation to affect the experiment. And so he'd put like a little hole in the garden shack, and he'd look at the garden shack through the hole, kind of through this telescope type thing into the garden shack, so he could see how much this mirror was deflecting the light. So he'd see the light be deflected slightly from the mirror as this rotate. And so he took measurements for, I think, over a year, looking into the hole, seeing how much the mirror is being deflected. It was just incredible for such a small number that he was able to do this experiment, and he gets big G within 1%, which is just crazy. No one was able to improve on that number for over 100 years. Just a phenomenal experiment, and the fact that he was so accurate was just extraordinary. Okay, so we have a lot to owe to Henry Cavendish, even though he was kind of a strange man. If you want to look up more about him, I recommend this YouTube video. It does a good job of explaining what the experiment was and how Henry Cavendish was. Okay, but that is all we covered in this week for gravity, and we will get into orbits next time. But hopefully that made sense. Again, the equation can be a little bit tedious at times, just plug in the numbers, but just make sure you get it into your calculator correctly, and you'll be just fine. But let me know if you need help with anything, and thank you for watching.